this video, I want to define the binomial distribution. So we need to start with the binomial experiment. A binomial experiment is n independent Bernoulli experiments. So we have a set number of times we want to perform some Bernoulli experiment. In this case, our random variable x is given by the total number of successes. As an example, we could flip a coin 5 times and record the number of heads we received. Some notation with binomial distributions. We'll say a random variable x is of the form bin in P, so bin for binomial. This tells me that my variable x is binomial with n trials, and P is the probability of success. In this case, my probability mass function is given by the probability that x is equal to x, which will be the combination in Cx times p to the x 1 minus p to the n minus x. And this distribution has expected value given by np, and variance given by np 1 minus p. Physical traits such as eye color are determined from a pair of genes, with one gene inherited from the mother and one from the father. Each gene can either be dominant, D, or recessive, R. So people with gene pairs DD, DR, and RD are alike in that physical trait. And we want to assume a child is equally likely to inherit either of the two genes from each parent. And if both parents are hybrid with respect to that particular trait, I want to find the probability that 3 of their 4 children will be like their parents with respect to this trait. So the idea of hybrid means that each parent is going to be DR or RD, although these do function similarly. So we're going to assume both parents are DR. This tells us that the possible children would be DD, a D from the first parent and R from the second, R from the first parent, D from the second, or an R from each. So my probability of success, there are 3 that are alike out of a total of 4. So that's our value for P. We want the probability that 3 of their 4 children will be like their parents. So I want the probability that x is equal to 3. In this case, n is equal to the total 4 children. So we have 4 choose 3 times p to the 3 power 1 minus p to the 4 minus 3 power. And when we work that out, we get approximately 0.422. So there's a 42.2% chance that 3 of the 4 children will be like their parents. Let's suppose 70% of all purchases in a certain store are made with credit card. And we're going to let x denote the number of credit card uses in the next 10 purchases. I want to find the expected value and variance. Well, the probability of success, the probability they've used a credit card, is 70%, or 0.7. And the total number of experiments we're looking at is 10. In this case, the expected value is equal to n times p, or 7. We should expect about 7 people to use the credit card out of the next 10 purchases. The variance is given by n times p times 1 minus p. 1 minus 0.7 is 0.3. And if we work this out, we get 2.1. So the variance of this particular binomial distribution is 2.1. Let's once again suppose that 70% of all purchases in a certain store are made with a credit card, and we're going to let X denote the number of credit card uses in the next 10 purchases. So we just said in this case P is 0.7 and N is equal to 10. I want to find the probability that 5 is less than or equal to X is less than or equal to 8. So I need to start with the probability of 5. That would be N, choose 5, times P to the 5th, times 1 minus P to the N minus 5. So that would just be 5. I also need to include 6. So we have 10C6 times 0.7 to the 6, 0.3 to the 10 minus 6. We also need to consider 7. So this time we have 10 choose 7, 0.7 to the 7, 0.3 to the 10 minus 7. And finally 8, 10 choose 8, times 0.7 to the 8, 0.3 to the 10 minus 8. And if we work this out, we get 0.873.